Okay, now you can start typing your names in the chat box. That will be considered for attendance. Okay. So in the previous class, we discussed about, we basically carried some general discussion regarding basic electrical engineering, right? Do you have any doubts on the previous discussion related to examination, etc., etc.? Okay, so if you don't have any doubts, okay, probably we can start with the course itself. Fine. So now let me take the course introduction itself. Okay. When we say basic electrical engineering, okay, what is that first thing that comes into our mind? What could it be? Basic electrical engineering. What is it basically? We say basic, that means to say the fundamentals, electrical engineering. Now, this basic electrical engineering, can be best explained with the help of a simple block diagram. No, okay. Now, why am I proposing this block diagram? Is that if you look at any appliance, it could be refrigerator, TV, fridge, etc., etc. Any appliance can be converted into this particular block diagram. Okay. Now, the basic electrical engineering, okay, system basically consists of some source, some load, and some controlling mechanism. Okay. So first, let me draw the block diagram. So block diagram of in short, basic electrical engineering system. Okay. You will have a source. Okay. This source is then connected to some controlling mechanism like switches. We all have operated the switches. Switch. Okay. And this switch is then connected to the load. You're able to hear me, right?
Yes, sir.
Yes, sir.
For a while, there was ping.
Yes, sir.
Okay, I thought I must have lost you. Fine. So this is the block diagram. You will have a source, you will have a load, and source and load are connected with a controlling mechanism such as switch. Okay, and everything is connected with the help of connecting medium. Okay, so all these three devices communicate with each other with the help of connecting medium. Okay, so these connecting mediums are nothing but wires, okay, made up of copper or aluminum. Okay, so this is the basic block diagram of basic electrical engineering system. Okay, now taking this block diagram, what we can do is we can discuss about what do you mean by source, what do you mean by switch, what do you mean by load. Okay. Now, in the level 1 explanation, we have proposed the basic block diagram. Now, in the level 2 explanation, probably, we can slightly raise the complexity, and we can draw the engineering symbols. Okay, we can draw the engineering symbols for source, switch, as well as load. Okay, so what I will do in the second level of explanation, I will draw the circuit diagram of basic electrical engineering system. Now, while drawing the circuit diagram, I have to take an example, because in the universe there are umpteen examples, right, for electrical system: fan, light, geyser, etc., etc., television. There are so many. So what I will do, I will consider a simple fan controlling mechanism. Okay, my example going to be a simple fan controlling mechanism. Now, how the fan is connected to the source? Can anyone tell me how it is connected? What are the intermediate elements you will find?
So the switches and the wires.
Right, switches and the wires, right? And you will have a regulator to control the speed. As of now, we will keep that regulator aside. Okay, so regulator will help us in increasing or decreasing the speed. We will keep it aside. Okay, so as your friend mentioned, it is basically consisting of uh, the switches and the load, right, along with supply. Okay, so let us first mention the supply. So this is how we describe the supply in terms of electrical engineering, or in terms of, I mean, it is common to any other circuit branch as well. Okay, since we are using single phase AC supply at homes, okay, you will mention P and N. P refers to phase terminal, and N refers to the neutral terminal. Neutral. Okay. This is then connected to a switch. A simple switch. Okay, this is your switch. You can perform on and off operation. Okay, if you put it down, the circuit gets closed. If you push it up, the circuit gets open. Okay, fine. Then we will also provide some fuse, right? There will be some fuse, right, in your circuit. So this is your fuse. Okay, protective device. And this is your switch. Okay. And then, it gets connected to the load. So this is your fan. Okay. The two terminals I have drawn: phase terminal of the fan and neutral terminal of the fan. Okay. This is your fan, and these are your copper wires. So this is the simple circuit diagram of a fan, right? So fan is considered as the load. Okay. Here it is. This is the load we were talking about, right? So that load is nothing but this. Okay, in the first level, we had mentioned load. That load is nothing but the fan. Okay, in the second level explanation. Okay, and the source we spoken about, right? We spoke about source, and that source is over here. Okay, now the source is nothing but the voltage, right? So the voltage level for our domestic application is 230 volt, 50 hertz, single phase AC. So this is the description of the source. 230 volt, 50 hertz, single phase AC. Now remember one thing. This 230 volt is the RMS value or the effective value, root mean square value. So any appliance, okay, which works on single phase voltage, okay, if you look at, they will have some voltage rating, 230 volt, or sometimes even 100 bar 230 volt, in the sense that particular appliance can work for 110 volt level voltage as well as 230 volt level voltage. Okay, whether they mention or not, they don't, it is always considered as the RMS value. So RMS value is the go-to value in our day-to-day operation. Okay, so 230 is the RMS value. Okay, fine. Next, let's come to the frequency. F is equal to 50 hertz. I'll just put a question mark because I need to ask certain questions regarding this frequency as well. Okay, I'll come to it little later. Okay, after the source, what do we have? We have a switch. Okay, so this switch is here. So this switch gives either logic 1 or logic 0. Logic 1 means current flows. Logic 0 means no current. Okay, that means to say either it allows the flow of current or blocks the flow of current by providing either closed path or open path. Closed means there will be a flow of current. Open means there will not be any flow of current. Okay, so it's a controlling mechanism. So switch basically acts like a controlling mechanism. Okay, and then you have fuse element. Okay, fuse is a protective device. I think you must have heard about it. In case of abnormality, okay, what will happen is the fuse element gets blown off, okay, or the fuse element gets damaged. Okay, so due to which it protects the costly appliance. The cost of fuse is about 5 rupees to 10 rupees, whereas the cost of fan will be in terms of thousands of rupees. So it is better to sacrifice less expensive component than the expensive component. That's the reason this fuse, sometimes also called as sacrificial device. Okay, it commits suicide in an attempt to protect your what do you say, expensive load. Okay, in simple terms you can say. Okay, it commits suicide before this guy goes to dead state. Okay, so that's your fuse. Okay, there are what you say, alternate elements for fuse, which is called as MCB. Okay, we will not talk about MCB at this particular juncture. Okay, so this is your basic electrical system. Okay, any doubts in this?
No, sir.
No. The same concept you can apply to any other system. Okay, in place of fan, what you will have is a television. In place of fan, you may have your light connected. Okay, the circuit diagram remains the same, only the load keeps on changing. Okay, fine. Yeah, so we have proposed a basic block diagram of basic electrical system. Now let us look at the explanation regarding source and the load. Okay, switch I will not discuss any further. Okay, it is enough. It's a controlling mechanism which either gives zero logic or logic 1. Okay, now let me talk about source. Have you come across term called source? If yes, can you name a few sources? Yeah.
So
What do you mean?
I'll give it a try. I think it could be that something that provides us the energy.
Right. Correct.
For example, batteries could be solar energy, something.
Yeah, exactly. So the sources are nothing but the energy providing devices. Okay. So these sources, okay, are also called as the active elements. Active elements. Okay. Now, let me come to this active element and passive element sometime later. Okay. I will also write passive elements here. Before actually giving the definition of active and passive element, first let me ask you, what do you mean by a circuit? Every now and then we use this word called a circuit, right? What is it consisting of? Circuit, what is it consisting of? It is consisting of these elements. We have already given an example for a circuit. This is an example for what? See, circuit diagram I have written, right? That means to say it's a circuit. Okay, what is it consisting of? This circuit is consisting of several elements. It is consisting of a source, it is consisting of a load, then it is also consisting of wires, fuses, switches, etc., etc. Okay. Now, basically, circuit is a combination of different elements. Combination of different elements. Now, when you say elements, okay, broadly, in electrical engineering, you can classify the elements into two types. You can classify them as active elements, and you can also classify them as passive elements. Okay. Now, these active elements, as the name suggests, they are active in nature. Active in the sense they are able to give the energy to the other elements. In the sense they possess, okay, so they have energy on their own. Okay. And it imparts energy on the other elements. Okay. As your friend mentioned, a battery or a solar cell. Okay. So there will be potential within the battery, or there will be some potential within the solar cell. The moment you connect, let's say, a bulb, what will happen? There will be a flow of electrons and the bulb will start giving out the light energy. Okay. So example for active elements are sources. Okay. And what do you mean by a source? Source is a element which possesses energy on its own. Okay. Now, example for sources, as some of you have already listed in the chat box. Okay. Cells, batteries, you have written. Cell and battery is the same. Okay. So let me write cells or batteries. Okay. Fine. Are there any other batteries? When you say cell or a battery, you can have what you say, lead acid battery, or you can have zinc chloride battery. You can have, say, alkaline batteries. Okay. You can also have solar cells, fuel cells, etc. Everything comes under cell category. Each one will have its own advantages and disadvantages. Okay. So this is an example for source. Any other examples can you give me?
Generator.
Exactly. Generator. Generator gives energy, right? Generator. Good. Okay. Generator also is an example for, source. Okay. Fine. Now, under generator, you can have different types. You can have AC generator. You can have DC generator. Okay. Now, under cells, can we have AC cell and DC cell? Okay.
Only
These Yeah, these cells are always DC. They give direct current electricity. Okay. So under sources, you had given me a couple of examples, right? Now, in these examples, we had seen that you can have a AC source as well as you can have a DC source. So that means to say these sources, okay, are broadly classified into two types: AC source and DC source. Okay, sources are elements which possess energy on their own, and these sources are classified into two types: AC source and DC source. Okay. Now, when I say source, you can either have a current source or you can have a voltage source. Voltage source. Okay. Now, voltage sources are readily available. Readily available in the market. For example, batteries. Okay. Or generators. You can also go and buy a generator. Let's say DC generator. I mean, what do you say? IC engine generator. All what you need to do is top it off with diesel, and it starts producing electricity. Okay, generators, etc. So these are all voltage sources. What about current source? Have we come across any current source? No, we haven't come across any current source. That's because you cannot go to a shop and ask for give me 2 ampere current source or give me 10 ampere current source. Okay, the current sources are derived from voltage source. Voltage source for specific applications. Okay, and those applications could be transistor control, etc. So only for sophisticated applications we go for current source. Okay, now let us not go into that direction, but of course, being an introductory course, you can always give classify. Okay, you can classify the source into current and voltage source. And you can also say that current source are derived from voltage source and which is meant for specialized applications such as transistor controls, okay, constant current controls, etc. On the other hand, voltage sources are readily available in the open market in the form of batteries and generators. Okay, and the sources are available in both the categories. It is available in AC category as well as it is available in the DC category. Okay, fine. Now let us propose the symbol. Okay, propose in the sense I'm not doing from my own knowledge. Okay, the universal symbol to represent AC sources and DC sources. So first let me consider AC sources. Okay, AC sources are normally represented using this symbol. Okay, this symbol. So this is for voltage source. Okay, on the other hand, if in case you have current source, then it is okay, rather this way they will represent. This is your current source. Okay, current source. So the pointed arrow gives the symbolic representation of current source. Okay, current source, and this sign symbol talks about the nature of the current source, that is AC source. It belongs to AC category. Okay, so this is how you represent the voltage source as well as the current source. Okay, remember all these voltage sources and current sources are active elements. Okay, then we have DC sources, which you have already used in your 11th and 12th. Okay, a DC voltage source can be represented with this particular symbol. Okay, one big terminal and one small terminal. Big terminal stands for positive potential and the smaller terminal represents the negative potential. Okay, this way you can present, or you can also present in this way. And you can draw a circle and put plus and minus sign. Okay, you mention it as E or V, doesn't matter. Okay, don't worry about it. Either E or V you can use. So this is the representation of, okay, I will write DC voltage source. And this is AC source. Okay, DC voltage source. On the other hand, the DC current source can be simply mentioned with the help of an arrow, and you don't have to mention any sign symbol over here. If you don't mention the sign symbol, it is understood that this is DC current source. Okay, DC current source. So this is the source representation. Okay, but in our regular class, we will be just talking about the voltage sources alone. Okay, AC voltage source and DC voltage source. We'll not be talking about any current sources, because current sources are discussed in detail in electronics engineering as well as in electrical engineering. So in introductory course, you don't require it. Okay, and we don't use it in our day-to-day life as well. So that's the reason we are not going to discuss. Okay, so this is about the active elements. Okay, in other words, this is all about the sources. Okay, now let us talk about the second type of elements, which are called as passive elements. Passive elements. Okay, now in the example of circuit diagram of a fan system, okay, we have seen that there are some wires and there are some loads used, right? So this load, that is fan, which is considered as a passive element, and the wires, which is also considered as the passive elements, in the sense, in cold state, in the sense, or if you don't connect any power, okay, or any voltage to these elements, they don't carry any current. In the sense, they do not have the energy on their own. Okay, they simply take the energy from the source. Okay, the devices which takes the energy from the source are called as passive elements. In other words, passive elements are those elements which do not possess energy on their own. Okay, so they don't possess energy, instead they take energy from the active elements. So you can say that they don't produce energy, or they don't possess energy. Okay, or it takes energy from the active elements. This is better. It takes the energy from the active elements. Okay. Example: resistor, capacitor, and inductor. Okay. An uncharged capacitor will not have any energy. Okay, whereas if you connect a voltage, then it stores the energy. Okay, so you cannot consider it as a source, because on its own it doesn't have any capacity to store the energy. Okay, if you connect any voltage across the plates of a capacitor, then only it stores the energy in its electrostatic field. So on that note, you can call these these three elements, that is R, C, and I, inductor, capacitor, and resistors, as the passive elements. Okay, and in electrical as well as electronics engineering, resistors are defined with capital letter R, capacitors for capital letter C, and inductors are designated with capital letter L. L stands for inductance, and C stands for capacitance, and R stands for resistance. Okay. So these are the passive elements. Okay. Now, if let us say, first let us consider resistor. Okay, this is your passive element. Let us connect this passive element to some active element. Let us say some AC source I'll connect. The moment I connect this active element to this passive element, let me write down here, this is passive element and this is active element. Okay, what happens? There will be a flow of current. Okay, and it consumes power. Okay, it consumes the power. It doesn't gives the power, it consumes the power. So it consumes the power, and the power gets wasted in the form of heat. So that is the reason, in any device, for example, fan, if you consider, okay, after using the fan, if you were to touch the dome of the fan, you will find some amount of heat, right? So that heat is due to the consumption of power made by the resistance of the winding. Okay, so whenever there is resistance, there will be a heat generated. Okay, and this heat is considered as the wastage of energy. Okay, so if your fan is consisting of lesser resistance in its winding, you can say that your fan is more energy efficient. Okay, so that way, it is related. Lesser the heat generator, greater will be the efficiency of the appliance. Okay, so that's the reason, you can always compare the quality of two fans. Okay, let's say you buy a fan, let's say some Ramlakan fan from the open market, which is available for say 200 rupees. And you also buy a good fan, something like Crompton Greaves. Okay, both are having same rating of, let's say, 100 watts. Use these fans for about 30 minutes. Okay, and after the usage, just turn them off and just start touching the fan domes. Okay, you'll be surprised that the Crompton Greaves fan will have lesser heat. Okay, on the other hand, your not so good fan, okay, the B grade fan will have more heat generated. Okay, though you are purchasing the appliance for a lower cost, what happens is that on longer run, your Crompton Greaves fan is going to give you lesser energy cost compared to the cheaper fan. Okay, so always go for a device which is more energy efficient. Okay, in India, this energy efficiency can be judged on the basis of BEE rating, Bureau of Energy Efficiency. Okay, 5-star. Sometimes this tab will not behave properly. So 5-star rating, okay, is highly energy efficient. Okay. On the other hand, 1-star rating appliance is it will have very low energy efficiency constant coefficient. Okay, very low efficient. Okay. very low energy efficiency coefficient. Okay. Have you seen the ratings in your fans or water heaters? The stickers they paste, right? Few stickers will have 5 stars, few stickers will have 3.5 stars. Yes. So all these stickers are nothing but, the energy efficiency information. Okay, higher the star rating, costlier is the equipment, but on a longer run, it saves a lot of energy cost, or it reduces electricity bill. On the other hand, lower the star rating, the cost of the appliance will be less, but on a longer run, it will pinch your pocket by consuming more electricity, and you are likely to get more electricity bill on monthly basis. Okay, fine. So this is your resistive element. Okay. All right. Next we have, let's say, inductive element connected to an AC source. Okay. The detailed analysis we will do it later. Okay, this is your AC source. Okay, there is no resistance. So in case of a pure inductive element, okay, what will happen is it doesn't consume energy. Why? Only resistor consumes energy, and there is no resistance, hence it doesn't consume energy. But the supplied energy by the source, okay, is stored in its electromagnetic field. So energy supplied is stored in electromagnetic field. Electromagnetic field. Okay, so that's about your inductance. Okay, but one fact I have to tell you is that there is no pure inductance. Okay, because inductance is made up of conductor itself, right? Inductance is made up of conductor itself. Only the difference is that normally these conductors are, straight in appearance. On the other hand, inductors will have a wound nature. Okay, because of this wound nature, you can have greater magnetic flux density. So magnetic flux density can be increased due to this wound nature. Okay, but it will have some amount of resistance. That's the reason, though the ceiling fan, okay, ceiling fan or the normal fan, what you use it at your homes, is considered as inductive circuit. Okay, this inductive circuit will have small amount of resistance. You cannot avoid this resistance because that's the nature of the material. Okay, there will be some or the other amount of resistance present in the inductor, and that is the reason the fan will have some amount of heating in it. Ideally, there shouldn't be any heating. You should be having only the mechanical rotation, but you cannot avoid it because resistance you cannot avoid. It is kind of inevitable. So there will be some amount of heat generated owing to the small resistance present in the inductance. Okay, the same case holds good for the capacitor as well. Okay, when you connect a capacitor across an AC supply, okay, if at all the resistance of the capacitor is neglected, then energy supply is stored in the electrostatic field. Static field. Okay, electrostatic field. Okay, but the ideal elements doesn't exist in nature. That is the reason small r is present in every capacitor. In every capacitor. Okay. And due to this small resistance R, even when you use capacitor, okay, in your circuit, some amount of heat generated in the capacitor as well. So this resistance R is the contributing factor for the heat generation in a capacitor. So some amount of heat generated in a practical capacitor. Okay, in a practical capacitor. Okay, but we don't have any what do you say, straight appliance which is capacitive in nature. Okay, all our loads, okay, they are either resistive or they are either inductive. Okay, so we don't have any loads which is capacitive in nature. Okay, the capacitor is used as a circuit correction element, in the sense it will increase the power factor. Okay, I will come to it when I come to module 2 or module 3. Okay, you don't have any load which is capacitive in nature. Okay, all your loads are either resistive in nature or inductive in nature. Okay, can you give me any example for resistive loads? In the sense, the moment you turn on, there will be huge amount of heat generated. Do you have, or have you used any such loads?
Electric bulb.
Electric bulb, yeah, this is a, yeah,
Heaters and electric cookers.
Geysers, heaters,
Iron box.
etc., etc.
Lamps.
Lamps, yes, incandescent bulb, majorly
Iron
incandescent.
box.
Yeah, iron box, correct. So these are all resistive loads. Okay, so very easily you can identify. The moment when you turn on, there should be, you know, tremendous amount of heat generated. If there is good amount of heat generation, then they are resistive loads. Okay, fine. Easily you can understand. Iron box, okay, water heaters, etc. Okay, what about inductive loads? As I given in my previous explanation, in inductors, there is nothing like pure inductor. There will be some amount of resistance involved in every inductor. Okay, so inductive loads are also plenty. Okay, any rotating device is inductive in nature, because in order to have mechanical movement, there should be some rotating magnetic field. Okay, so all motors are inductive in nature. Okay, for example, fans, okay, and your hair dryers. Okay, hair dryers, what it gives? Air, right? And you know, you can generate air only with the mechanical motion. So if there is any mechanical motion, then only you can think of generating the air. Okay, so hair dryers. Okay, then water pumps. Water pumps. Okay, so these are all examples for your inductive loads. Okay, wherein inductance is high, okay, and R is low. Okay, that's the reason I'm writing it, because there is nothing like pure inductance. All the loads will have some finite amount of resistance. So that's the reason I have written very high L value and very low R value. Okay, so this is about your loads. Okay, so loads are majorly classified into two types: inductive loads and resistive loads. And there is no capacitive loads, but capacitors are used as corrective elements in circuits. Okay. Example, to improve the power factor. What is power factor? We'll discuss later. Okay. Fine then. So what we have done is we have given a broad. We have discussed about the circuit and the elements of circuit. Okay. Circuit is an interconnection of various elements, and the elements are of two types: active elements and passive elements. Active elements are those elements which possess energy on their own. On the other hand, passive elements are those elements which doesn't possess energy on their own. Instead, it takes the energy from the active elements. Example for passive elements are inductors, capacitors, and resistors. In case of resistor, the supplied energy gets wasted in the form of heat. On the other hand, in case of inductor, the supplied energy gets stored in the form of electromagnetic field. And in case of capacitor, the supplied energy gets stored in the form of electrostatic field. Okay, so this is the quick recap of today's session. Okay, so what I will do based on today's lesson, okay, I will frame 10 MCQ questions, and by Monday you are supposed to answer it. Okay, fine. So in the next class, we can start with Ohm's law. We can start with Ohm's law. Okay, fine. So some 8 minutes are remaining, so I will not talk with respect to the syllabus. Some general questions I will ask. Okay. In the beginning, you remember, right? Somewhere while mentioning the frequency, I paused and I just wrote 50 hertz and I put some 2-3 question marks. Yeah, right over here. Okay. Now, why I have put the question mark is that why are we fixing our frequency at 50 hertz? Okay. All right. Entire globe uses 50 hertz cycle. On the other hand, US uses 60 hertz cycle. Doesn't matter. Okay. 50 or 60 hertz doesn't matter. Okay. That's because electricity invented in US, okay, was at 50 hertz cycle. Okay. Since the electricity was invented at 60 hertz cycle in the US, they have continued to use 60 hertz electricity. Okay. On the other hand, in India, the electricity was first generated at 25 hertz cycle, and then it increased to 50 hertz cycle, and that's the reason we are using till date electricity at 50 hertz cycle. Okay. Now coming to the specific question, you can take your time. Okay. Probably you can tell me on Monday also. If you know the answer, you can tell me now also. Okay. Why 50 hertz or why 60 hertz? Why not say 5 hertz, or why not say 5 kilohertz? Okay, low and high. Okay, this 50 and 60 hertz, this is considered as some moderate. Okay, moderate frequency. So why are we operating at a moderate frequency? Why don't we operate at a very low frequency or very high frequency? Okay. This is the question. Okay, this is the first question.
Sir, I don't know the exact reason, sir, but then I find a correlation with the frequency in AC supply and games. Like in games, they use 50 to 60 FPS.
Okay.
And in games, like how they show the characters moving and stuff, it's at that rate. The graphics at that rate is quite good. If it goes too high or too low, it kind of behaves like funnily.
Okay, okay. That's the reason. I mean, those displays, the AMOLED or whatever display what you use, if it has higher refresh rate, the viewing experience will be better, right? It's like 90 frames per second display is better than the conventional 50 frames per second display. Correct? No. Great.
Yes, sir.
Yeah. Right. You're correct. You're correct. That is one way. You are talking about the visual part. That's correct. Also, little, you can dig deep to extract some other information as well. Okay, you are right. In the display technology, what you have mentioned is correct. So I have a question for you. Okay, so we have presently 90 frames per second refresh rate, right? It is indirectly related to the frequency. Why not 900 frames per second? You should get better viewing experience, right? If you increase the refresh rate to a very high value, theoretically you should get very good viewing experience. In the sense, you should not be having any motion blur thing.
Yes, sir. If the frequency is very high, it may lead to energy wastage through inductive and capacitive reactances.
Okay, right. Correct. So that means to say, you're saying that this frequency has some dependency on, I mean, the reactances have some dependency on frequency, correct?
Yes, sir.
Correct. That's the answer. That's the answer, actually. Okay. So, answer is reactance. Okay. As I mentioned in the beginning, most of the loads are either resistive or inductive in nature. A resistor will not have any frequency issues because resistance is independent of frequency. On the other hand, if you look at the other appliances, for example, your CFL lamp or your fluorescent lamp, okay, compact fluorescent lamp and fluorescent lamp, the trade name is tube light. Okay, so they are all RL circuits, in the sense there will be some resistance and major part is the inductance. Okay, so when you say inductance, we understand it in the form of the reactance, right? XL is equal to 2 pi FL. So that means to say this reactance is directly proportional to frequency. Okay, so what you can do is you can now correlate this frequency with the reactance. Okay, if your F is very high, okay, what will happen to XL? XL is high too. Higher the frequency, higher will be the reactance. Now, what is reactance? Reactance is nothing but opposition offered to the flow of current. So when XL is very high, what will happen? Efficiency is less. So if you were to operate at 5 kilohertz cycle, what would have happened is your appliances would have offered very high opposition to the flow of current. And due to this very high opposition, the efficiency would have been a lot lower. Okay, so if you operate at very high frequency, energy cost will go high. Okay, that's because it offers more resistance and more wastage of electricity. That means to say, energy cost will be very, very high. Okay, fine. So one part is dealt with. Why not low frequency? If you operate at low frequency, okay, since XL is directly proportional to F, if F is less, then XL will also be lesser, right? So that means to say it should be more efficient. Correct, no? Theoretically, it appears as though operating at a lower cycle will result in more energy efficiency. So that means to say your appliance becomes more energy efficient with the lower frequency, and you are expected to get lesser Okay, it's not energy bill, electricity bill. You're supposed to get lesser electricity bill. Okay, if so, why are we not using 5 Hz cycle? Okay, so think about it. The second aspect. Okay. Okay. All right. So first aspect your friend has already explained. Okay. The second aspect, that is by fixing lower frequency, what will happen to the circuit operation, that you are supposed to tell me in the next class, that is on Monday. All right. Fine. So I'll stop my class